So our first problem is a classic physics problem where there's a mass on a slope with friction. So here's our mass, has a mass of 6 kilograms, and it's on a slope of 40 degrees. And we want to know what's going to happen. Is it going to have any acceleration down the ramp? We don't know yet, because there's two different types of friction that we want to account for, kinetic and static. It must be greater than static, and then it'll start moving, and then once it does start moving, it's going to be kinetic. So we want to find that out. Our frame of reference here is really important. We want to make sure that we understand what we want. There's a couple of them that you could choose. You could just choose a regular X and Y. The one that follows gravity. Gravity, right, always goes straight down no matter what. And you have another force that could go this way. This is force normal. So those are our two main frame of references. And there's one more, and that one would be friction. Since it wants to go down, friction's going to go up. I'm going to leave out the kinetic and static because I don't know which one it is yet. So here are the three forces acting on the block. We want to know if it slides down. So we go, okay, what's my frame of reference? We could do Fn and force of friction because you'll notice that they're perpendicular, or we could do Fg. But the most important part is acceleration. We want to know which way it's going to move. So that's going to be our frame of reference. So we're going to make this our X and this one our Y. And I'm not sure how perfect I am, but that should be perpendicular. And we want to reference everything based on this. Now, force of gravity is at an angle, and it has both an X and a Y. So we want to break it apart into its components. So here is this F of G in the Y direction, and then here it's F at G in the X. Now the Y kind of makes sense because it's attached to this, but I'm going to move the FGX over here. FGX. Alright, so here we have three forces. Force of normal, which is opposite of the surface. We have force of friction, which is opposite of the motion or direction of motion. We have Fg that's broken apart into its two parts, Fgy and Fgx. You'll see really quickly Fgy and Fn are equal and opposite because this thing is not going up or down. Then the question is this one. Which one's bigger, Fgx or force of friction? That's what we want to find out in order to find acceleration. So we're going to use this as my new frame of reference, the x-axis, which is right there. So here is my equation I'm going to set up. Sum of all forces in the x direction is force of gravity in the x plus force of friction, which is equal to ma. And our goal is to find a. Unfortunately, before we even get there, we're going to have to do certain things. Okay. We need to break this apart because Fgx is technically, we need to be able to derive it from Fg. So here is the angle 40. We can move the 40 over here. And then Fgx will be, we'll put them over here, sine of theta, which is opposite over hypotenuse. So it'll be Fgx over Fg. And then the other one would be cosine theta, which is adjacent Fgy over Fg. Okay, so here's my relationships. I'm going to use that to figure out what these are. So I'm going to plug it in. Fgx is Fg sine theta. Force of friction is mu. I'm going to still leave it blank for now. Fn ma. This Fn is right here. So, like I said, these are equal and opposite of Fgy. So we're going to do that. So Fg sine theta plus mu Fg cosine theta equals ma. So here's my equation. I want to solve for a. So we're going to plug everything else in. And we know everything else. Here's the big deal. So we're going to find what Fgx is. So that is Fg, which is 60 times sine of 40. I'm going to leave mu here. I want to find out what this is. So this will be 60 cosine of 40 equals mass, which is 6 times acceleration. Now, normally, before you even go that far, we want to figure out what force of friction is. and which one we're going to use, whether it's kinetic or static. Remember, we always check static first, but the reason why I worked it out is we kind of need to know what this is. So right now, force of static is 0.8 times 60 times cosine of 40. So we want to know what this is. Now, the reason why I took it this far is we kind of need to know what this entity is too, because we need to compare it. Which one's going to be bigger? So let me grab my calculator, do both of these. Make sure you're in degrees versus radians. 0.8 times 60 times cosine of 40. And I get force of static friction of 36.77. Let me make sure I'm in degree, and I am. All right, now I'm going to do the same thing here. 60 sine of 40. And I get 38.57. All right, now this is my FG sine theta x, so that's this. This is bigger than this one, so we know it's not this one, but it's kinetic. So I'm going to do the same thing, but kinetic, 0.6 times 60 cosine of 40, and that one is 0.6 times 60 times cosine of 40. And that one is 27.6. So now I have plus 27.6 equals 6a. Now before I move on, I always like to do my sign check here. So FGX, we need to determine what do we want here, but they're opposites. So if you want to make this one positive, this one has to be negative. That's just how it works. And acceleration is going to be down, so that one's, hopefully it's going to give us a positive number. So we have that. So minus so here we get acceleration of 1.83 down the ramp, or positive because we made this one positive. So here we go. That is our answer. Next problem. This is another classic problem. Let me do a screenshot really fast. This is another classic problem. And this one is kind of an Atwood problem, Atwood machine problem. So here we have a table. On this table we have a pulley, and we have a mass right here attached to a string, which is attached to another mass right here. So remember, the strings, or tension, delivers the same amount of force, but it just pulls from opposite ends, or it changes direction. So here, force of tension's up, but here it's to the left. So it not only pulls in opposite direction, but also changes direction if there's a pulley. All right, so here we have a mass of 15 kilograms that's hanging over, that's attached to 60 kilograms. And it's right now velocity 0 because it's at rest. You have mu s, which is 0.2, and you have mu k, which is 0.1. So we want to know, what's the acceleration? When you do a problem like this, the first thing you always ask yourself is it moving? Okay, so in order to find out, we're going to label all the different forces acting on. On this one, Fg gives you negative 600. Then you have Fn, which is positive 600. Because there it's not going up and down, left and right, but it could go left and right. Up and down, it's not going anywhere, left and right it can. You have friction that wants to go this way because the direction of motion is to the left and down, and it makes sense because even if this has bigger force than static, it's still not going to crawl up. So negative, positive, negative, positive. Here you have force of gravity. In this case, it's 150 newtons. And then you're going to have tension keeping it up. And tension on this side. Okay, so we want to know, is it moving? So in order to find out, we need to find mu s. So force of friction static is mu s Fn. Mu s in this case is 0.2. Fn is 600. and you get 120 newtons. Here we have 150, so this one's bigger. So it's going to move. So force of kinetic friction is equal to mu k Fn. In this case, it is 0.1 times 600. So instead of 120, I'm going to get 60, I believe. So a little less. So now once we have that, we want to make sure we assign all the signs that are correct. This one is negative, this one is positive, negative, positive. So sum of all forces in my direction of motion is equal to a positive Fg minus T plus T minus force of kinetic friction. These cancel out. This is equal to ma. So Fg is 15 times 10, so 150. Force of kinetic friction is 60. And then the mass of these two together is 75A. So we get 90, I believe, if I did my math right, over 75 equals A. And you get 1.2. Now, in order to find the tension, you just look at one part of it. So it doesn't matter if you do the 15 or the 60. 15 is a little bit easier just because it's just Fg and tension. Fg here is, remember, negative 150. Here is, we don't know. Now, before I move on, acceleration is this way, and I labeled it as 1.2 meters per second. These two signs have to match. So if you're going to make Fg negative, this also has to be negative because the arrows are pointing in the same direction. So here we have sum of all forces. In the y direction, you have Fg plus tension equals ma. We know what a is. We know what Fg is. Negative 150 plus tension equals 15. And this time we only include 15 because we're just examining one mass. Acceleration was 1.2. And like I said, this needs to be negative. Then you just solve for t. 15. $132 newtons, and it's up, or in this case we labeled it as positive. So hopefully it makes sense. Tension is only 132, Fg is 150, so Fg is bigger, so it should go down. All right. So the first problem here is a car going around a curve. And in this case, there's no bank. So here's my car. Whoa. Here's my car. And its goal is to go around in this curve. So that means there must be some sort of force that's pushing it towards the center. In this case, it's going to be force of friction. Static friction is going to be the one pushing it to the center. So that's pretty much it. So you have force of static friction is equal to centrifugal force because that's the only force present. And if you kind of break it down, you have the following. So this is equal to mu s force normal equals mv squared over r. Mu s mg positive is mv squared over r. And then if you solve for v, what's the maximum speed? So you're going to have the following. M's cancel out. And you have r mu s, what am I missing? G square root equals v. So that's all you have to do. So in this case, the radius of the curve is 50. Mu is 0.15. And gravity is about 10. Now, before I move on, I did derive the equation, but you don't have to. You already know this from our notes. So you just plug it in and multiply. So inside the radical, I get 75. I'm going to take the square root of it, and I get 8.66. And since it's traveling around a curve, it's kind of hard to give it a sign. But I guess it's moving forward. Now, if we double the mass, would the maximum speed increase or decrease or stay the same? And the answer is it's going to stay the same. And the reason is because when you look up here, on both sides you have masses. On both sides the masses cancel out. So it doesn't matter how big or small something is. It's going to experience the same kind of centrifugal force. So here we don't have to worry about mass. Now, if we do have a bent curve, and this is when you need to bust out your notes, let me pull it up really fast so everybody can see it. So in our notes, we were able to derive this thing right here. And that's the equation we're going to use to solve this problem. Alright, so here's the equation, and I'm going to write it down because I forget it all the time. Rg sine theta plus mu cosine theta divided by cosine theta minus mu sine theta. Alright, so here is our equation. We want to know what's the maximum speed. It has a bent curve of 20, and we know everything else already. So the radius was 50, gravity is 10, sine of 20 degrees plus the mu, I believe, was 0.2, but let me double check. 0.15, so I was wrong. 0.15 times cosine of 20 divided by cosine of 20 minus oops. Alright, so now we have everything and we just need to solve for v. Make sure you take the square roots, make sure you distribute and not make a stupid mistake. I'm going to try my best not to. So we have sine of 20 plus (0.48). You have cosine of 20 minus 15 Alright, so I simplified this one, now I'm going to multiply this and divide by that. So here we go. So 50 times 10 times 0.48 divided by 0.123888, and you get a velocity of 270. And you take the square root of that, and you get 16.44 meters per second. So that is the fastest you could go with the following conditions. All right, last one. All right, so this is the last problem we have. This was kind of the first problem we did in class, and this is kind of the ride. I can't even remember. Gravitron. So it spins, spins, spins. The floor drops out on the person, and the cool part of it is the person stays against the wall. And if they're really crazy, they can stand on the wall as it goes around in a circle. So we're going to kind of answer this in terms of variables this time, but it doesn't really have to be. So here we have this, and then I'm asking how many forces are acting on the person, and there's going to be 3. You have a force normal. I don't know why it does that all the time. You have a force normal, which is always pushing in from the wall. So as it spins around, it's always going to be towards the center. So force normal is acting as if our central force. You have force of gravity that's always there, F of G, and then to counter force of gravity, you have friction. In this case, it has to be static because you're not moving. So those are the 3 forces acting on the person. All right, now how much force? Actually, I did one thing. Okay, it says calculate the force the ride must exert to keep them in place. So you have Fn that has to equal Fc, right? So you have mv squared over r, which is equal to Fc, whoops, the wrong one. You have Fn, which is equal to mv squared over r. Okay, so if you go too slow, though, something happens. You have to make these 2 equal and opposite, right? So here we also have to be considering that Fg has to also equal force of static friction. And this is where the relationship comes in. Fg is mg, and force of static friction is mu sfn. So here is the condition. In order for this to work, normally it's just Fn equals this, but in this case, you don't want gravity to be bigger than force of static friction, so they have to relate to one another. Both the x and the y do. So you're going to move this over or substitute that in. So you have mg equals mu s mv squared over r. So this is the relationship. If you want to know what kind of force. Oh yeah, I already did that. And then we have the following. So here we have these 2 together. And then if we solve for v, will be the slowest that you could go. If you want to find other aspects of it, you can. So the masses cancel out. And then we want to solve for mu in this case because that's what we want to do. So Rg equals mu SV squared. I'm going to move the v squared. So Rg divided by v squared equals mu. So if you want to find the lowest mu possible, then you just plug everything in and then you'll be good. Yeah, I'm going to sneeze. I'm going to pause. All right. So let me just recap. 3 forces. What kind of force is keeping it into a circular path? That's force normal. Force normal does have a condition on it because gravity is pulling down on the rider. So we need a force of friction pulling it up or pushing it up or something. So you make them equal to each other. Fg equals force of static friction. Fn equals Fc. And then in order for us to kind of solve and break it down into some more simpler variables, you substitute mv squared into Fn. And then you're able to find this relationship right here. And from that relationship, you could either solve for mu or v, technically r2 if you have certain things in constant. Now, our last problem is more conceptual than mathematic. So here we have a rider that's going, instead of horizontally, they're going vertically. So we want to know, okay, so what's happening here? Well, if we look at it from the other point of view, you have a circular path. You have a person that is upside down here, on its side here, and here. Our concerns can be top and bottom. In all of the cases, you have to have centrifugal force pushing towards the center. Now down here, gravity is against you, so that force normal needs to be bigger. Now on the top, gravity is working with you, so force normal is in addition to instead of subtracting. So here they're in opposite directions, so they work against each other. In order for this person to stay in a circle, Fn has to be bigger. Here they're working together, so they're just depending on the relationship as you're spinning. Now as you're going slower and slower, because the question is, how's the slowest you could go? Well, as you go slower and slower, Fc is going to get smaller and smaller. Now Fg cannot get smaller. You have a certain amount of mass, no matter how fast or how slow you are, you still have the same amount of mass. Fn, though, can change. So what could happen is Fc could get so small that it's only Fg. So that's the goal. Fc equals Fg. Now, if it's any smaller than Fg, what's going to happen is the person's going to fall. So this is the absolute slowest you go. Any slower, Fc is going to get smaller than Fg, and then the rider's going to fall. So here we just kind of substitute everything with mv squared over r equals mg. And once again, the m's cancel out, so you're just left with v squared over r equals g. And if you want to look for the speed, you just solve for it. V squared equals rg, v equals square root of rg. And that's it. All right. Message me or email me if you have any questions. I apologize, I'm a bit tired, so I might have just stared at the screen for a little bit, trying to figure out what to say, but other than that, that's it.